Hi all, we are here to present the movie recommendation web app. So in this project, we deploy an open source model via web service that helping user give movie recommendations. So user have the flexibility to input either a movie description directly and then click generate get recommendation, or they can input some keywords and then click on generate description to allow the large language model to fill in the rest of text. And then next step is clicking on generate recommendation. So the system will provide recommendation for the movie choice. As we can see here, outside in the movie name, we also have rating, main stars, votes, and genre. So with this app, user can see what movie they want to watch based on the text they input. And through the project, we also containerize our service with AWS ECS and Fargate. We also implement a CI/CD pipeline that automate the testing and deployment stage for our project. And then we will move on to the architecture diagram.
And here's the architecture of our project. What we did is first import the data from IMDb, and then we generate the embeddings based on the description of the movie using Rustbird. And then we store the embeddings in Qdront. How it works is that user input their keywords or descriptions into our index page. If it's a description, it will generate embeddings using Cohere. If it's a keyword, then it will first generate a description using OpenLlama, and then the description is used to generate embeddings. Then it will compare the embeddings generated based on the user input and the embeddings we have for the movie description. It will return the most relevant movie result and return the movie information on the result page. Both the backend and the frontend is contained in a Docker and deployed using ECS Fargate. Besides, we use AWS CloudWatch to monitor the performance of our website. And then we'll get deeper into each part.
So the dataset we are using for this project is the IMDb movie dataset. It contains a rich compilation of movie information. We clean the original dataset by merging movies from various categories. We create a consolidated genre column and filtered release between 2020 and 2023 to ensure data relevance. We retained essential attributes such as movie ID, name, year, rating, description, director, and star for further analysis. So the resulting dataset has more than 30,000 rows stored as combined data CSV. As an overview to set up the project dependencies, we begin by initializing the project with cargo new and signing up for Qdront to establish our vector database cluster, along with Cohere for obtaining an API key for generating embeddings. The environment variables are stored in a .env file and exported, after which dependencies are added in the cargo toml file and built using cargo build. And finally, we create a combined data JSON file containing columns from the movie data CSV. So the project incorporates our robust open source LLM model called Rustbird to understand movie descriptions from the movie database. And using the LLM model, the movie descriptions are transformed into vector embeddings. It helps to capture the nuanced content for the later embedding similarities analysis. We did 2 local testing, which encode descriptions into embeddings and print results. So after the local testing of the Rustbird LLM model is successful, we move on to the data ingestion process for the Qdront vector database. It involves several key steps outlined in the setup final RS script under the SRC folder. Initially, the script reads movie records from a JSON file and computes sentence embeddings for movie descriptions using Rustbird. These embeddings, along with other movie data, are then stored in a Qdront database. We can check the task collection in the Qdront dashboard. And as we can see, the Qdront cluster now have our collection filled with associated embeddings or points. And next, we are going to go over the detail of how generating recommendations in this project.
So in order to generating description and recommendations, we use our main.rs file to helping us. So in the main.rs file, we import necessary libraries, and then we define data structures. Then we move into 2 main functions. First one is movie. So it take a movie description as input from our front-end HTML page in through the post request, and then it perform inferences using Cohere API, and then retrieve the movie detail from Qdront, and then return HTML page with the movie information. And our next function is generate text. It also handle it with post request and take a JSON object containing a movie description and then generate text using OpenLlama LLM model, and then it returned the generate text. We also have two infer function that helping us linking and serving the purpose of those two main functions up there. And with that in mind, we move on to our front-end implementation.
For our front end, we use HTML to create the index.html, which gives us the front page of our website. For the result page, we're using HTML generated within our main.rs file, which send the recommendation for users. And now let's move on to the deployment stage.
Yeah, so first I'm gonna go over the CI/CD for our project, where as you can see over here, it's successful and it passed. So basically here, I'm just going over a brief overview of it, where we first use a Linux image to build our project and make sure it's lint format test successful, and we build it. And then here we commented it out because it takes very long, but essentially this will work in a sense where we use the Docker and Docker image, where we build a Docker image to upload to ECR. We also did this with Docker, with a public repo, where you can see over here where I'm using a public Docker image that I push myself. And yeah, so to deploy the website, we use the AWS GUI, where we first create a VPC so we can expose our website to a public IP address, where you can see here it's LLM test VPC, it's exposed here. We then create a cluster in Elastic Container Services, and we then create a task definition here where we can specify how much memory and how much CPU can be used for our container. We then go back to the cluster, and then we are able to run a task every time. And this goes back to continuous deployment, where no matter what we push, we are able to, it points to the latest Docker image. So once we run new tasks, it will always auto deploy to the newest image. Going back to the metrics, we can see over here, we have CloudWatch enabled, where we can see the various metrics that's being used. So here you can see, if I refresh really quickly, you can see that an example of us using of the model being loaded in the backend and seeing how we're logging it. And yeah, thank you for your time, and I appreciate everyone here. Thank you, Noah Gift, and hope you guys like our website.